Let's begin with basics of problem formulation, as it is very vital and it's where everything begins. In this stage, we usually start with a question like, is it possible vehicles can be driven by themselves? Which type of additional product must be provided to somebody once they check out? Or how much storage can be provided to client from data center within a given time frame? In problem formulation, we look into questions if they help in maximizing business values like, should I know which type of product customer is likely to buy which is valuable from business point of view? Or which type of product will be trendy for holiday so that they can be stocked well in advance before the holiday arrives? Or it could be as simple as knowing your client and customer's habit and preferences. All these questions are going to have very good impact on businesses if they can be thought from business point of view. One of the great issues with problem formulation is correctly recognizing problems and challenges which can have business impact and focus on recognizing correct possibilities and opportunities. For example, consider self-driving vehicle. How many people believe in that the driving vehicle manually is a big issue? Probably not many. In reality, this is not a concern in the conventional sense of the term, but there's an opportunity for its automation. Creating self-driving car has an enormous opportunity. This does not mean that there is no problem or perhaps challenges are not associated with this opportunity. One part of the problem formulation phase is to identify those possibilities where machine learning can be used. In order to use machine learning efficiently, one may need to ask several questions such as, is machine learning suitable for this business use case? If yes, how it can be resolved by ML? If not, define a reason for not solving the same by using ML. What kind of ML problem it could be? If it is, then define a success metric with clause and try to make success metric fit to the business use case. What kind of ML problem is this? Classification or regression? And finally, is data appropriate for ML? The next set of questions can be around the feasibility of leveraging cloud infrastructure. We might ask the question if cloud implementation is suitable for this problem, or the on-premise implementation is much more useful. So to answer the last question specifically, we need to know what are the advantages of using cloud implementation over on-premise and vice versa. Most ML problems in their initial phases, which is exploratory data analysis, might not require heavy computation, and thus handling them on-premise would be more beneficial. However, moving to modeling phase, it might become essential to move to cloud since you might require more powerful CPUs and GPUs to run models in shorter time frames. This can be considered as one of the alternatives to cloud, which is called as on-prem data center, or it has all compute capacity that you might need to solve ML problems. This could be a better approach since clouds can be very costly and their total cost of ownership are usually very high. In that scenario, if you need 24/7 compute capacity, it will be better to use on-premise data centers. Another benefit of this approach is privacy. There might be some sensitive data which as a company you're not comfortable putting on cloud, or it could be compliance or government rules that might stop you from putting data in cloud. Hybrid solution can also be a good alternative to cloud. Data scientists can run preliminary model test on premise and then training and deploying production grade models in cloud. Hybrid way of infrastructure is always easy on cost and can easily adhere to compliance and privacy. Now let's look into some general pointers that may help you decide if you should go to cloud solution. Access to the newest hardware at the click of a button, flexible resource usage and extendable in the peak times, decoupled architecture by not being restricted by any specific hardware. Now let's discuss one of the most widely used cloud platform for machine learning, which is Amazon Web Service SageMaker. Let's see some of the important features. It has the most complete and comprehensive platform for handling data science projects. AWS has many different configuration of machines available called as EC or Elastic Compute Instance, which can be used for any machine learning load. You can very easily build, train and deploy models using SageMaker. It also helps you in managing different scales of data and their operations. And lastly, they have production-ready, already trained models for various problems like speech recognition, recommendation, computer vision, and much more. Finally, let's look into some points that may be considered as best practices. Ensure that the data and computation endpoints, either on-premise or on cloud, remains at the same location. You wouldn't want to have to transfer data from on-premise to cloud or vice versa for any computation need. For structured data, use a pre-processing step that first dumps the data into flat files. Files offer a persistency layer for database queries and thus improve version control and reusability when you're training the models. And finally, let data scientists concentrate on data science, not DevOps or MLOps. Let's revisit the question that we proposed in the previous section. These questions will help you to formulate your problem efficiently as follows. Is machine learning suitable for this problem, and why or why not? What is the ML problem if there is one, and what would be a success metric look like? What kind of ML problem is this? And finally, is the data appropriate? Now we'll discuss these questions with more details. In machine learning world community, some people are passionate about machine learning and they do have misconception about machine learning that it can solve almost every problem. However, that's not the case because machine learning has its own limitation and constraints. Financially, building a machine learning algorithm can be very costly and there are possibilities that outcome of ML algorithm may not have business value as per the requirement. For example, building a real-time recommendation engine with outstanding performance for a small retail website may cost good amount of resource to company at some extent. However, there is a possibility that the scale is not big enough to afford the price of the expenditure. There are some rules which can be imposed on recommendation, but it may have business value and are simpler and cheaper. Cloud for machine learning projects have various advantages, that is spending up the computation time, faster GPUs, etc. However, business needs to take decision whether the cloud service should be used or not on the project due to costly affair. Hence, business should take these facts into consideration while processing for machine learning implementation on their project. Technically, although there is a lot of data in world today, unfortunately most of these data are unlabeled and unstructured. This is to say, initialization of machine learning projects on this data would require good amount of human force for labeling and structuring, which might add some burden on project budget and possibly may not provide good ROI initially. Let's discuss another key note which is very meaningful while building machine learning projects. Those are called metrics. The point to note here is metrics needs to be predefined for the technical measurement to monitor machine learning models. These metrics named as recall, precision, F1 score, and accuracy. Business and data scientists should provide business meaning to these metrics in advance to develop better understanding on these metrics. Let's discuss the following case. For a churn prediction model, below is the confusion matrix. This gives us the following scores, which is precision equals to true positive divided by true positive plus false positive equals to 90.9%. Recall is true positive divided by true positive plus false negative, which is equal to 95.23%. Then after doing some experimentation using different set of hyperparameter, we reach the following set of metrics. Precision, which is 85.7%, and recall, which is 96%. If you notice these results, we can say that the second set has higher recall and lower precision. However, the question arises here is, which metric is acceptable and which one should be rejected for the chosen business application? If we closely notice, second model is costly to the business compared to the first model, and let's take a look why. Second model has 20 false negative, that is to say 20 customers shall be retained in the business and there is no deviation that they can be noticed as churners. This is to say second model is pretty costly compared to the first model. In other words, the technical evaluation metric may not always provide the real business benefit and business might need to think more towards the businesses. That's all for this video. Thank you. Now let's emphasize the idea of problem formulation and how it's drastically affecting the whole project. Amazon recently initiated advertisement to its clients when they check out the company's website. The director wishes the advertisement to be customized to the consumer as possible. You have access to all the customer data and list page information. Do you think machine learning is suitable for this problem? The answer to the previous question is that machine learning is suitable for this application due to the below 3 pointers. First is scale, second is range, and third is speed necessary for this application. In the real world scenario, there is enormous number of ads that needs to be served to the million of consumers, which is supposed to be popped up at the earliest as they enter and access the website. Now let's look into how we create a formulation of problem which we just defined. Popped advertisement should be relevant to the consumer. The essence of this problem is that if ads aren't useful to the clients, Amazon as an organization wastes the chance of clicks on their websites along with the wasteful visit of customers with the nuanced advertisements. So question arises here is, how Amazon can serve the most relevant promotion to its retail clients and generate a profit. This is to say, popping up relevant promotion to clients will have a higher chance of revenue generation, and that can be called as higher success rate if clients purchased popped up items. This is being called as supervised learning problem due to availability of labeled past purchase data. And the data is appropriate enough because web page interaction of individual visits, that is number of clicks, staying time on the web page, number of scrolls, item classification, customer log data on the given websites are available with Amazon. Let's discuss another use case. Imagine there's a business which manufactures headphones and sells directly to large and small electronic emporiums. As an effort to increase pricing, which is supposed to be competitive, Store A and Store B determined to develop the pricing details for every headphone company and the product of theirs, which is approximately 240 products, and they do want to release regular products. You're going to have all the specification from each manufacturer as well as the product rates. Imagine sales has a dip due to some external factors, hence first concern of manufacturer shall be find a competitive product and lower price compares to the flagship product of that manufacturer. For this case, the question is, can we handle this issue by using machine learning approach? ML is probably not necessary for this. We can just search the dataset to see which headphones are priced lower than the flagship, then compare the feature. In other words, it's more of an apple-to-apple comparison. Let's take another example. Imagine you're working as a senior product manager at Ridesharing company. By market research, you were successful to collect good amount of customer feedback data and found that customers and users and drivers are not satisfied with the behavior of your organization's application. The specific feature which allows customers to put a pin exactly where they would like to be picked up is a major issue here. The customers say motorists hardly stop at the pin area. Drivers say customers frequently place the pin in an area where they cannot stop. Your organization has a relationship with the most frequent use map, which means you control the existing relationship by getting immediate backend access to the data of driver and customer, which basically includes the longitude and latitude of individuals along with the visual picture of every traffic delay and along with the regulation information if available. Now, the conventional question, do you think ML is useful for handling this problem? The answer is yes, and let's see the reasoning. The first two options is scale and automation. ML is appropriate because of the scale and automation involved. It's not feasible to drive everywhere and write down all the places that are feasible for pickup. However, by using location maps, longitude and latitude, we can predict whether a location is suitable for pickup or not. And the last is clear success metric. Here we can define success metric pretty easily, where we can identify pickup location as well as these location can be integrated into the features based on longitude and latitude requirement. That's all for this lesson. Thank you. In previous section, we have discussed about business aspects, problem formulation, and ML usability. In this section, we will walk through the Amazon review use case and understand in detail. Suppose you are working for a startup that concentrates on delivering on-demand video streaming services to users from all around the world. Your company wants to introduce movie or show recommendation based on their viewing history. You were asked to solve this problem by leveraging machine learning to create recommendation engine. Let's discuss about the dataset. Amazon Customer Review Dataset is a collection of reviews on different products from Amazon.com marketplace between 1995 to 2015. Customer reviews are one of the most important data for Amazon. Collecting and showing reviews has been part of Amazon culture since the beginning of the company and is arguably one of the most important source of innovation. For more details on this data, see Amazon Customer Review Dataset. This exercise focuses on review of videos. The video dataset contains 1 to 5 star rating from over 2 million Amazon customers on 160,000 digital videos. These details contain features collected by Amazon, Marketplace, which is a 2-letter country code, Customer ID, which is random customer identifier, Review ID, which is unique review ID. Next is Product ID, which is Amazon's standard identification number. Product parent, which is parent of an ASIN, multiple ASINs could be possible here. Product title, the description of the product. Product category, which is a broad product category. And star rating, which is product rating starting from 1 to 5 stars. Let's see some of the more column names. First is helpful votes, which is number of helpful votes in a review. Then we have number of total votes in the review, which is total_votes. Then we have wine, which is whether the review was written in wine. Then we have review_, which is review details, where the actual reviews are stored. And then finally verified_purchase, whether the review was verified or not. In many ways, recommender systems were a catalyst for the current popularity of machine learning. One of the Amazon earliest success was customers who bought this also bought this feature. The $1 million Netflix prize spurred research, raised public awareness, and inspired numerous other data science competitions. The recommender system can utilize a multitude of data sources and machine learning algorithms. Most combine various unsupervised, supervised, and reinforcement learning technique into holistic framework. However, the core component is always a model that predicts a user rating or purchase for a certain item based on the user historical rating of similar items as well as the behavior of other similar users. The minimal required dataset for this is a history of user item rating, which we have as part of the data. We will walk through by building recommendation engine based on above discussed data. Also, you might have noticed that the dataset is stored in S3 bucket in AWS Cloud Services. That's all for this video. Thank you. Now that we are aware of a problem to build a recommendation system, we will try to figure out how recommender systems really work and which approach is being followed by engines. A recommender system is a technology that is deployed in the atmosphere where elements like products, films, functions, articles are being highly recommended to owners like customers, app users, visitors, and readers. Usually, you will find several users and lot of things present in the environment, making the problem difficult and costly to resolve. In a store, a good merchant knows that individual preference of customers. Her and his excellent recommendation make customers happy and increase profits. In the case of online shopping and marketing, personal tips will be produced by an artificial intelligent merchant, which is what we refer to as recommender engine. Now let's look into different types of recommender systems. The first is content-based methods, where we define a model for user-item interactions, where user or item representations are given explicitly. The next is collaborative filtering method, where in the first variation of it, model-based, we define a model for user-item interaction, where user and item representations have to be learned from interactions matrix. The second variation of it is referred to as memory-based, where we define no model for user-item interaction and rely on similarities between users or items in terms of observed interaction. The last type is hybrid method, which is mix of content-based and collaborative filtering approaches. Content-based filtering uses product features to suggest some other things such as what the person likes based on the previous action of others, or perhaps explicit feedback. To demonstrate content-based filtering, let us find several functions from the Google Play Store. The following figure shows a function matrix in which each row represents an app and each column represents a feature. Features may consist of different types such as education, casual, health, etc., the publisher of the app, type of a technology, and many such like that. To simplify, believe this feature matrix is binary. A non-zero value usually means the app has that characteristics. Users can also be represented in the same feature space. Some of the users related features should be explicitly provided by the users. For example, a user selects entertainment apps in their profile. Other feature can be considered as implicit, which is being installed previously along with the main application or during the update. Now let's see what to do for setting up recommendation engine. The first is to pick a similarity metric which is defined. Second is to set up system to score each candidate. And the last is that each model is trained on a specific user without information about the users. Like any machine learning approach, it has some advantage and disadvantage. Here are some advantages. The model doesn't need any data about other users since the recommendations are specific to this user. This makes it easier to scale to large number of users. The model can capture the specific interest of user and can recommend niche items that every few other users are interested in. Also, it has some drawbacks. Since the feature representation of the item is hand engineered to some extent, this technique requires a lot of domain knowledge. Therefore, the model can only be as good as hand engineered features. The model can only make recommendation based on existing interest of the user. In other words, the model has limited ability to expand on the user's existing interest. That's all for this video. Thank you. In this video, let's address some of the limitations of content-based filtering. One thing to note here is that it uses similarities between users and items simultaneously to provide recommendation. This allows for recommendation, that is, collaborative filtering models can recommend an item to user A based on interest of similar user B. Furthermore, the embeddings can be learned automatically without relying on manual engineering of features. Let's take a movie recommendation example. Consider a movie recommendation system in which the training data consists of feedback matrix in which each row represents a user and each column represents an item, which is referred to as movie. The feedback about movies falls into one of two categories. First is explicit, where users specify how much they liked a particular movie by providing a numerical rating. And the second is implicit, where user watches a movie, the system infers that user is interested. To simplify, we will assume that the feedback matrix is binary, that is, a value of 1 indicates interest in the movie. When a user visits the homepage, the system should recommend movies based on both the similarity to movies the user has liked in the past, and the second is movies that similar users have liked. When building a user-based collaborative filtering algorithm, we are measuring the similarity between the users. If user A is similar to user B and like a movie X, then the user B is likely to like movie X. Hence, user embedding says, follow the approach few times, which is representation for all the users. For the item-based collaborative filtering approach, if we say that movie X is similar to movie Y, and then they received the same rating from the same user, hence by following this approach, we got the item embedding matrix based on item representation. Below are some of the advantages. The first one is no domain knowledge is necessary. We don't need domain knowledge because of the embeddings are automatically learned. Second is serendipity. The model can help users discover new interests. In isolation, the ML system may not know the user is interested in a given item, but the model might still recommend it because similar users are interested in that item. And the last is great starting point. To some extent, the system needs only the feedback matrix to train a matrix factorization model. In particular, the system doesn't need contextual features. In practice, this can be used as one of the multiple candidate generators. It also has some disadvantages. Let's see what. It cannot handle fresh items. The prediction of model for given user item pair is dot product of the corresponding embeddings. So if an item is not seen during the training, the system can't create an embedding for it and can't query the model with this system. This issue is often called the cold start problem. Now let's look into the alternative for this, which is hybrid recommender system. To overcome the cold start problem, we usually build a hybrid model that can combine these two models and use the advantage of building a content-based system, which has no problem at all with the cold start, then build another collaborative filtering system that can be enhanced over time to receive best accurate prediction, combining both the approaches. That's all for this video. Thank you. In this video, we'll look into AWS Storage Services, which are simple storage services like S3, Elastic Block Store EBS, Elastic File System EFS. Amazon Simple Storage Service, commonly referred to as Amazon S3, is an object storage service that offers industry-leading scalability, data availability, security, and performance. This means customers of all sizes and industry can use it to store and protect any amount of data for a range of use cases such as data lakes, websites, mobile application, backup and restore, archive, enterprise application, IoT device, and big data analytics. Amazon S3 provides easy-to-use management features so you can organize your data and configure fine-tuned access controls to meet your specific business, organizational, and compliance requirement. Now let's look into Amazon Elastic Block Store, which is referred to as EBS. EBS is an easy-to-use, high-performance block storage service designed to use with Amazon Elastic Compute Cloud (EC2) for throughput and transaction-intensive workload at any scale. A broad range of workloads such as relational and non-relational databases, enterprise application, containerized application, big data analytics engine, file systems, and media workflows are widely deployed on Amazon EBS. You can choose from 6 different volume types to balance optimal price and performance. You can achieve single-digit millisecond latency for high-performance database workload such as SAP HANA, or gigabyte per second throughput for large sequential workloads such as Hadoop. You can change volume types, tune performance, or increase volume size without disrupting your critical application. Next, let's look into Amazon Elastic File System. Amazon Elastic File System, referred to as Amazon EFS, provides a simple, serverless, set and forget Elastic File System that can let you share file data without provisioning or managing storage. It can be used with AWS Cloud Services and on-premise resources and is built to scale on demand to petabytes without disrupting application. With Amazon EFS, you can grow and shrink your file systems automatically as you add and remove files. Amazon EFS offers you the choice of creating file systems using standard or one-zone storage classes. Standard storage classes store data within and across multiple availability zones. One-zone storage classes store data and redundantly within a single AZ at a 47% lower price compared to file system using standard storage classes. Amazon EFS offers 4 storage classes, 2 standard storage classes, Amazon EFS Standard, Amazon EFS Standard Infrequent Access, and 2 one-zone storage classes, which are Amazon EFS One Zone and Amazon EFS One Zone Infrequent Access. Amazon EFS is designed to provide massively parallel shared access to thousands of Amazon EC2 instances, and AWS containers and serverless compute services include Amazon Elastic Container Service (ECS), Amazon Elastic Kubernetes Services (EKS), AWS Fargate, and AWS Lambda, enabling your application to achieve high levels of aggregate, throughput, and IOPS with consistent low latencies. For most applications, you'll be dealing with S3 buckets. Thus, for the next videos, we will deal with AWS and read data from them. In this demo, we'll see how to read files through Amazon S3 bucket and then load the data into Notebook instance. If you want to know how to create a Jupyter Notebook instance on Amazon SageMaker, please follow this link. This link has a bunch of different steps that you need to perform, starting with logging into your console. Please go through the steps so that you have a Jupyter Notebook instance available. Once the instance is available, the very first thing that we'll do is we'll import some important libraries. We'll start with import OS and subprocess for terminal commands. We'll import warnings to disable all the warnings that will come in the code. For handling the tabular data, we'll import pandas. For handling matrix data, we will import NumPy. To import any SageMaker packages, we will import SageMaker, and we'll also import SageMaker.mxnet, which is one of the models available. Boto3 is a library which will help us access SageMaker and AWS functionalities, which we'll import as import Boto3. Then for handling JSON, we will import JSON. And then to handle visualization, we'll import matplotlib.pyplot as PLT and import Seaborn as SNS. We will also add this to display all the outputs in the cell and not just the last one. And finally, to ignore the warnings, the import warnings that we have done, we'll use filter warnings to ignore each and every warning. The very first thing that we're going to do is we'll start by bringing the dataset from Amazon S3 public bucket on this notebook environment. What we are doing here is we are having the base path and the file path. So base path covers where the data folder is and the file path is exact name of the file. If that is already not created, we will first check that. If it is not, then we will create that. If it is, then we will just simply say file already downloaded. So you can see that in our case, it is already downloaded. Once we have that, we then try to read it through pandas read CSV. The above code, you can notice that this will throw error because we are not including error bad lines equals to false. This dataset has some bad rows with different numbers of columns. So this will throw an error if you don't include error bad lines equals to false. Once you do that, you can actually see that Pandas actually throws in warning saying that there are some lines where you can see that Pandas basically throws you an error telling you that there are some lines where it was expecting it to be 15 fields, meaning 15 columns, but it actually saw 22. So do remember to make sure that you have error bad lines equals to false. Once this runs, you can very simply see that the moment we do df.head, we get to see the overall data that we are trying to load. So in this data, you have customer ID, you have review ID, you have product IDs, you have product parent, you also have product categories, the rating that somebody has given to this particular review. And if you go towards the end, you will see that you have the headline of the review and the body of the review. So the body of the review is actual review, and we also have the date of it. This is the data that we will try to do lot many things in our coming demos. In this particular part of the demo, we just wanted to load through S3 bucket and load it in Pandas data frame into a Jupyter notebook. In this video, let's continue to explore our dataset that we have used in our previous video. In previous video, you have seen how we loaded the data from Amazon S3 and then we started playing with the data. In this video, let's further investigate. To start, let's first check the shape of our dataset. To do that, you can simply do df.shape, and that shows you roughly around 4 million rows and 15 columns. Let's look closely to every column of our dataset. To do that, we can simply run a for loop with df.columns and print the head of that df.column. We are also printing a separator, which is a double dash, so that you can quickly see what are the top values separated by those double dashes. As you can observe, there's no obvious error in the data, but the review date column needs to be in the correct format. To do that, we can simply use pd.toDateTime and pass the column with the df dot, and this will help us get the column in the proper datetime format. To do the check, we can simply do df.dtType, and you can quickly check that now the review date is in the correct format, which is datetime 64. Now let's quickly check how many null values you have in the dataset. To do that, you can simply do df.isNull.sum. What this will do is it will give you a total number of null values for each column. As you can see that these three columns have some amount of values which are null, and we would like to address that in the next code. To do that, we can simply use df.dropNA, which is one of the functions available to drop all missing values. And we're also using inPlace equals to true, which will inPlace, which means that in the data frame itself, it will do that change so that you don't have to save it back to a new data frame. Now let's check whether this change has been done properly or not. So we can run the same command, which is df.isNull.sum, and you can see that how now we don't have any values which are null in any of the columns. Now our dataset is ready for subsequent processes. In this video, let's look into Amazon SageMaker. Amazon SageMaker provides a suite of built-in algorithms to help data scientists and machine learning practitioners get started on training and deploying machine learning models quickly. Here's a quick cheat sheet for Amazon SageMaker Supervised Learning. The algorithms that are present as built-in algorithms for predict item categories are factorization machine, KNN, linear learner, and XGBoost. Similarly, for predict numeric or continuous variable, you have factorization machine, KNN, linear learner, and XGBoost, which is very similar to predict item category. If you have to predict future behavior based on past event, you have deep AR forecasting, which is available as part of Amazon SageMaker. Please refer to this cheat sheet if you want to know what specific service and models to use for Amazon SageMaker. Let's look into the cheat sheet for unsupervised learning. If you have to drop columns with weak relationship to target, you can use principal component analysis as a built-in algorithm. If your plan is to detect abnormal behavior, you can use random cut forest and IP insights. If you're trying to improve data embeddings, you can use object to vector. If your goal is to do group similar object, you can use internal inbuilt k-means. And finally, if you're trying to organize documents into topic, you can use algorithms like LDA and TM. Let's look into the cheat sheet for SageMaker textual analysis. If you're trying to assign predefined categories to document, you have blazing text as a service. If you're trying to convert text into another language, you have sequence to sequence model. Same is with summarizing a long text, you have sequence to sequence model. If you're trying to convert audio to text, you have again sequence to sequence. And finally, for image processing cheat sheet, if you're trying to label an image based on content, you do have image classification algorithm. If you're trying to detect people and object in an image, you do have object detection algorithm. And finally, if you're trying to tag pixels individually with a category, you have semantic segmentation available as built-in algorithms. When dealing with SageMaker, it's always a very good idea to use one of these algorithms that we just discussed because they are very compatible with SageMaker and they are optimized and efficient. Always keep any other algorithm as a second choice. That's all for this video. Thank you. In this course, we have discussed topics about problem formulation, cloud versus on-premise implementation, recommendation systems, practical tutorials, and finally SageMaker built-in algorithms. Coming up next is data preparation and SageMaker security.